engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
Discoveries.
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to the Naked Scientists podcast. This is the programme that brings you the biggest breakthroughs and talks to the major movers and shakers in the worlds of science, technology and medicine with me, Chris Smith. Coming up, the UK follows Australia with a social media ban for the under-16s. But does this work? Also, scientists trace the history of cotton. Where did it come from in the first place? And the Trillionaire Club. Elon Musk sits by himself as the sole member at the moment, but how do you actually spend that much money? The UK is following Australia in banning under-16s from accessing social media. The restrictions, which will come into force at the start of 2027, apply to platforms like Snapchat, TikTok, YouTube and Instagram, on top of limitations on live streaming and some AI chatbot functions for users who are under 18. UK Prime Minister Keir Starmer says the move will help to give kids their childhood back and improve online safety. But the proposed policy has sparked a debate about whether it will improve the mental health and well-being of young people at all. Sander van der Linden is a professor of social psychology and society at the University of Cambridge.
It's important to sort of separate digital technology in general from social media because they are a bit different. But kids are increasingly interacting with digital technology. They're on social media. They're getting their news primarily from social media. I think most of the time we're talking about the sort of group from 13 to 17 is what most of the concern is about, I suppose, because, you know, when you're 18, you're technically an adult, and the ban that's being proposed is for under 16. So that's kind of the age range that we're talking about. And an increasing share of those kids are spending the majority of their time online.
And what's the concern that proposing bans is trying to address?
I think the concern is that there's online harms on social platforms like Instagram and TikTok, which are particularly popular with that age group, that children are exposed to inappropriate content. That could be wellness scams, it could be fraud, it could be extreme violence, it could be mis and disinformation, it could be cyberbullying, it could be sexualized images. So there's a lot of content on those platforms that is not appropriate for children, and those are broadly referred to as online harms. And the question is whether exposure to that type of content is negatively impacting their mental and physical health.
Well, that's what I wanted to ask you, is there an evidence base? Or are we kind of groping into the dark saying, well, kids are doing this and they're doing it in increasing amounts and therefore it's likely to have harms, so we'll ban it? Or have they actually got objective evidence that this has happened and now this is an outcome?
For years, there was only correlational data. So they would do these big studies asking teens about their mental health and then about their social media habits. And they would find small negative correlations that, you know, the more time you spend on social media, the lower you score on indicators of psychological well-being. But then people said that doesn't prove causation, doesn't prove that the social media companies are the cause of this negative relationship. So then experiments were done as best as you can to try to randomize assignments to social media or detoxing studies, trying to get people to log off for a certain period. And they do find causal evidence that when people, particularly kids, log off, that it can lead to improvements in their mental health and also in their thinking about media and other people, and there's less exposure to negative content. So there's an evidence base there. However, and this is where the other side comes in, social media, unlike other harmful products that people tend to reference, like smoking or drinking and so on, social media also has benefits to young people. And those effects have also been demonstrated, that sometimes they feel less lonely, they feel more connected, they feel better about themselves, and they feel that they can get access to support groups, neurodivergent groups, for example, or LGBTQ plus communities. And so social media also allows for self-expression, to join social movements, engage with geopolitical issues. So there are studies that show that youth also benefit from social media. And then when you do the big meta-analyses and systematic reviews, what you find is that there there are negative impacts and then there's positive impacts, and then the net effect is a bit muddled. And that's what's getting everyone worked up is that, people so say, well, there's negative effects that we need to counteract. And then there's people say, yeah, but there's also positive effects. So how can we eliminate the harms while preserving the benefits? And I think the Prime Minister has decided that the harms outweigh the benefits.
They've chosen age 16 as a cutoff. In recent years, some people have been surprised by data showing that, in fact, the human brain develops well into our 20s. So people are still going to be affected by anything they do until they're in their mid-20s. So is 16 the right age?
I think 16 is relatively arbitrary. The developing brain, what you see is that young adolescents are more risk-seeking, they have less self-control, and they're more influenced by what their peers are doing. So there is a risk profile of increased susceptibility that's pretty well established that social media companies, because of the way the algorithms are maximizing engagement and attention, are explicitly exploiting. So there is a potential combination there that I think does warrant cause for concern. But then the question becomes, what is the right age? The problem is that the current age that is already there, which is 13, is not being effectively enforced. Right? And so moving it up to 16 just raises the question, if you can't enforce it really at 13, how are you going to enforce it at 16? And you're quite right that the brain develops well into our 20s. And so what is the right age?
One country that's tried to go down this path is Australia. They've taken an age-related approach, but interviews with youngsters there suggest that as many as 2/3 are circumventing the restriction. So it's therefore only hitting or affecting a third, and they might not be the most vulnerable ones. So do you think then that the best approach is to hit the content? That means going after the companies that make the platform, because those can then police the content better.
I think so. And for once, most of the scientists are actually in agreement that the scientific evidence doesn't necessarily support a wholesale ban proposal. But it is politically popular because parents are concerned. It's an easy solution that doesn't require complex regulation and focusing on content and so on. So I think it's a bit of a knee-jerk reaction. And the age question is a moral intuition that we want to protect very young children, which makes sense, but the age is totally arbitrary in terms of how it's decided. As you've said, in Australia, they're getting around the ban because teens will do what they do best, which is, ignore rules when they're being imposed. So the Prime Minister made a statement on, I think it was Good Morning Britain, about how he knows that they're going to try to get around it, and that's fine. He just wants to introduce some friction to make it more difficult. He knows teenagers are drinking beer, but the fact that it's illegal just makes it harder, and that's all that they want to do. And I think there's I can see the sentiment in that approach, but I think most researchers would argue that bringing the focus back on technology companies and their content rather than kids is actually the better angle, because what we want is safe and clean feeds for kids, which requires strict regulation on the types of content that and functionality that are appropriate for kids. So no autoplay, no auto infinite scroll, no stranger messaging, PG rated feeds, no sexualized content, stuff like that. That can be regulated, that can be enforced, and then kids can still use digital technology and not be exposed to any of the harm.
It's a thorny topic, isn't it? Be interesting to see how that plays out. Sander van der Linden there. Antibodies are sticky molecules that circulate in the blood and also seep into body fluids where they can attach themselves to potentially harmful microbes and immobilise them. Traditionally, we've thought of this happening either by them flagging up the pathogen to other elements of the immune system for destruction, or by blocking key parts of the bug that it relies on to grow, spread and cause disease. But now scientists at the MRC Laboratory of Molecular Biology in Cambridge have uncovered an additional way that antibodies can work inside our cells. Leo James and Tyler Rhinesmith have discovered that when a microbe decorated with antibodies invades a cell, the antibody triggers an intracellular alarm system that directs the cell to build a barrier around the invader and then dump it into the cellular equivalent of the recycle bin. This generic mechanism could, they think, offer us new ways to make antiviral and antibacterial drugs and maybe even find a cure for the common cold. Leo first.
What we knew was that antibodies will stick to the surface of something like a virus, but the virus can still enter a cell even though those antibodies are there. And the antibodies essentially hitch a ride, so they enter the cell alongside the virus.
So the question becomes, when you have a situation like that with a microbe which has been able to invade a cell and it takes an antibody with it, does that antibody do anything once it's inside the cell?
Exactly. Can that antibody then do something to stop the microbe from copying itself, from replicating?
Did we used to think that once that situation was arrived at, really the antibody's not doing anything because by then the bug is inside a cell? Or had we always suspected that maybe it was functional, but we just didn't know how?
So it was previously thought that the way that antibodies would work would be by interfering with the entry of the microbe into the cell. But once the microbe was inside, the antibody was then useless. It couldn't do anything further.
So Tyler, how did you actually try and probe this then to find out if antibodies hitching a ride, like Leo says, inside cells do anything when they get there?
One of our kind of favorite techniques in the lab is to turn off genes inside a cell and then ask how that affects a particular process that we're interested in. So in this case, how antibodies around a virus may or may not interfere with the ability for that virus to replicate inside the cell. And then what we did was we took this pool, this population of cells that had genes individually turned off in each of them, and we infected them with an adenovirus, which we had coated with antibodies. And then we asked whether these viruses coated in antibodies were prevented from infecting the cells.
Your hypothesis then is if we've deleted or turned off a gene which is doing something linked to that process, we should see a difference.
Yeah, that's exactly right. So if you lose a gene that's important for preventing infection, the cell that has lost that gene will become infected. And through that, we can learn which genes are important for that process.
So this is a sort of resistance mechanism normally. If the antibody stuck onto that adenovirus is doing something in the cell, it ought to, if the cell is responding appropriately, help the cell to defend itself. Disable that process and you'll just get a runaway mine train.
Yeah, that's exactly right. Yeah.
Is that what you saw, Leo?
Yes. So for a normal healthy cell, when it's infected with adenovirus in the presence of an antibody, those antibodies do a good job of stopping the virus from replicating. But in Tyler's screen, what he saw was that there were a number of cells with knocked out genes that had lost this ability and become fully infected. And so we could ask, what are the genes that are required to allow this normal process to work?
And obviously from a gene, you can ask, well, what does that gene do? And that points you towards whatever machinery the cell is using that gene for.
So one of the clever things that Tyler did with his data was not just to look at the kind of individual genes that were being knocked out, but then to look to see whether there was anything that those genes had in common. And so what he was able to see was that actually those genes that were most important, i.e. that when they were removed, the cells were becoming infected, what he found was that a lot of them belonged to a single process in the cell, something that we call autophagy. And it's one of the systems the cell uses in order to get rid of unwanted material.
So it's like a garbage disposal / recycling system.
Exactly. So what happens in autophagy is that the cell first needs to label what it wants to get rid of. And then once it's labeled it, it starts to build a special membrane around the material it wants to recycle. It then takes that compartment, I guess that kind of garbage can with the garbage inside, and then it moves that garbage can into a sort of giant recycling machine where everything inside it can be chopped up into pieces and then recycled and reused by the cell.
How does the antibody being there make a difference to that?
So the antibody is the key part of the process because normally if a virus infects a cell, the cell is blissfully unaware that it's there. So the virus can then happily go on and replicate and kill the cell. The antibody plays the key role because it acts as a flag. So by labeling the virus, the cell knows the virus is there because it can see the antibody. And so the cell produces a very special protein called TRIM21. And it's this protein TRIM21 which sees the antibody. And as soon as it sees the antibody, it can alert this kind of whole system of machinery that this is garbage that the cell wants to get rid of.
Now we know this, is there a way of either tooling it up to make it more effective to get rid of intransigent, hard-to-manage infection, or dial it down in order to stop situations where the immune system might be overactive and that is contributing to disease?
Yes, this is exactly what we're thinking about next. So now we understand about how this natural system of immunity works. Can we learn from it to actually design antiviral molecules and therapeutics that we could use to treat disease? What we know now is that there's a system here where antibodies are providing the labeling, and then TRIM21 and autophagy is providing the machinery. Sometimes viruses and bacteria can evade those antibodies, and so they enter the cell without the label. If we had a way of designing and making drugs which could provide that labeling function that the antibodies have, then we could make them visible again to the immune system and allow TRIM21 and autophagy to then block them. And so this is something that we're very excited about as a potential future antiviral therapeutic.
Maybe even a cure for the common cold, if you can make that work, because that's the big problem, isn't it? And if you can make this work for the rhinoviruses that plague us every winter, we might sniff a bit less.
That would be fantastic, and it is a fabulous goal. But we're a very, very, very long way from being able to cure anything. But do we think we could come up with molecules that could be effective? Yeah, potentially, if we can use this natural system.
Leo James and Tyler Rhinesmith with that absolutely fascinating finding that antibodies also work inside our cells. They just published that discovery in Molecular Cell. And let's hope they crack that cure for the common cold soon.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
This is the Naked Scientists podcast with me, Chris Smith. Still to come, Elon Musk joins a club of one, the Trillionaire Club. But what could you do with £1 trillion? Before that, though, over 25 million tonnes of cotton are harvested every year, accounting for about 25% of the textile industry. But where did this crop plant come from in the first place? Because it doesn't exist in the form we're familiar with anywhere in nature. The answer is that our ancestors somewhere over in Mexico unwittingly bred it for us over 5,000 years ago. By picking and cultivating ancestral plants that had progressively more of the traits they wanted, early farmers in the Yucatan Peninsula slowly evolved the strains that we rely on today. Jonathan Wendell at Iowa State University used the power of genetics to solve the ancient mystery.
Well, so you go and you look at cotton row crops, and there's these beautiful fields of stunning white cotton pretty much growing on the outside of the plant, because it's when the fruit opens, it reveals all these cotton fibers. But it's not a wild plant in the United States or anywhere else where cotton is grown. This is a product of human selection, just like that ear of maize. So I wanted to know, where is it in nature? What's it look like in nature? And by extension, what happened when we turned it into a modern crop?
Well, can we start with the when first and then work forward from there? So when did we actually first get cotton as you and I would recognise it?
To the best of our knowledge, about 5,500 years ago.
And did they recognise what they were playing with? Were they using it for textiles, or did it have some other use and has subsequently been press-ganged into the textile industry?
The wild forms that humans would have first encountered are not useful for textiles. In fact, those white cells, the cotton fibers that you see in the modern row crops, they don't exist in nature. What exists in nature are plants with much, much shorter, maybe only 1 centimeter long, dingy, dark, brownish fibers that you can't spin into threads and yarns. They were probably collecting them and using them for local household needs, such as candle wicks, pillow stuffings, wound dressings, things like that. Actual textiles didn't come along till much, much later.
How have you therefore sought to try and understand how we've arrived at the plant we do have today and how it got from that starting point to that?
First, you have to know what that starting point was. And that's what took us to the present study, because we didn't really know what wild cotton was. It's presumably pretty rare in nature. Nobody knew in the literature. So for the last 40 years, 50 years, various collectors, including myself, have been collecting all the relatives in the wild that we could find and sort of figure out who's most closely related to the crop plant. And once we can identify who's most closely related, we have a good model of the actual ancestor.
And that's looking at genetic relatedness. What proportion of my genetic letters are similar in me to this other one that looks like me?
Right. So what we ended up doing is we ended up collecting hundreds of plants and over the years sequenced thousands of genomes, the whole genome, and each genome is the size of the human genome almost. So in each of those genomes, you can compare them to one another and you can find which of them are most closely related to those of the row crop that dominates world cotton commerce. In doing that, you're basically lining up all the DNA sequences. At each individual site, there's 4 possible states. We call them A, T, G, and C. And you find all the similarities and you find all the differences. And you can use bioinformatics and computational biology to figure out who's most closely related to whom.
And where does this point to an origin then? How does that then lead you to where it came from and how it came to be?
We collected these plants from throughout the potential wild range in the Caribbean islands, the southern part of Florida, the Yucatan Peninsula of Mexico. It's basically, these plants are in the Caribbean basin on the drier sides of all the islands and on the drier sides of the mainland parts of the Caribbean basin. So we collected plants from throughout that range and we sequenced the genomes of all these plants. Then we also went into cotton crop fields from all over the world and we sequenced those genomes too. So then when we compared that pool of wild plants to that pool of cultivated plants, it clearly pinpointed the origin of the wild cotton gene pool in the northwestern part of the Yucatan Peninsula of Mexico.
Because we know how fast things evolve and we know how fast things change from one genetic form to another, you can get some idea of the genetic clock that's ticking here. You can look at how things must have converged to arrive at that place. What does the time clock say? Does it line up with the archaeology?
The time clock for these wild perennials turns out to be, from a standpoint of population genetics, very few generations between the wild forms and the modern forms. I mentioned maybe 5,000 years in the archaeological record, thereabouts. So we don't get very precise estimates from a molecular clock standpoint. We kind of have to depend on the combination of genetic differences and archaeology together. But let's just say those pieces of evidence are congruent. They tell the same story.
It came along pretty quick then, didn't it? Have we any idea how or what forces would have driven the plant to evolve the way that it did? Was that purely people just picking ones that had a bigger yield because that was what they wanted and that concentrated the genes that have led to the plants looking the way they do today?
The answer to that involves two things. We can look at the selection forces and we can look at what those targets were, even though the people who were doing the selection didn't know anything about genomes thousands of years ago or DNA, no idea. They could practice selection. They wanted better plants. They wanted more cotton. So yes, they would pick the best representatives, and this is a form of natural selection. We call this selection under domestication. So it's directional selection too. People are picking things that are bigger, better, more flowers per plant, more consistent blooming, easier to harvest, longer fibers, stronger fibers, ultimately whiter fibers. Each of these becomes a selection target. Each has a different underlying genetic basis, and they're all happening simultaneously. So it turns out that thousands of genes were targeted by humans without knowing it.
Jonathan Wendell, and that study just came out in the Proceedings of the National Academy of Sciences, USA. With his net worth receiving a rocket-powered boost from the recent flotation on the stock market of his SpaceX venture, Elon Musk has become the world's first trillionaire. In fact, he's already hundreds of billions of dollars better off than when he recently became the sole member of the club because of a significant surge in SpaceX's share price in the aftermath of the public offering. But just how rich does this make him? And is it actually possible to even spend that much? We put in a call to the economist and author Vicky Price. Vicky, how many noughts are there after a trillion? Because this is going to be a new word on some people.
12, I'm afraid. So loads and loads and loads of zeros afterwards. And you need to just make sure that it is just 12 and not more, because then, of course, it just makes the whole calculation a little bit more confusing, because it all moves in threes normally. So if you try and calculate a billion, that's 1,000 million. And then when you calculate what a trillion is, that's another 1,000 billion. That's basically where you end up.
It's an unthinkable amount of money, isn't it? I mean, if you were to put that in context, how does that compare economically with, say, a country?
Well, I'm speaking to you actually from Greece. So a trillion is something like 3 times, if not more, the size of Greece in terms of GDP. And of course, for everyone who watched England versus Croatia and was so pleased about England winning, of course, Croatia is even smaller than Greece, and it's something like 4 times a trillion of the country's GDP, of Croatia's GDP. So it is huge.
And is the UK, our national debt, something like 3 trillion, isn't it? So Elon Musk could basically pay off a third of our mortgage.
Well, he can do all sorts of wonderful things. He can pay all these things that we want, defense or welfare and so on, and not worry about it at all. The only thing, of course, to bear in mind is that he doesn't actually necessarily have this money to hand. I mean, he's rich because a lot of the shares that he owns in his company are valued at a certain amount, and therefore it's his wealth that's there. It's not that he gets that money every day, if you calculate what it would mean per month, that he can then use for other things. But of course, he can use that value of his company to borrow more money and then use that as income on which he pays no interest, if that is what he does, and then use that indeed to pay back our national debt. That would be nice.
Yes, indeed, because you can leverage assets to raise money against them, and you've effectively realised some real hard cash. But because you've made no sale to get that capital gain, I suppose there's no tax in that, is there?
Absolutely, there is no tax, and quite a lot of suggestions that are made to tackle the fact that we've had such a big increase in the number of billionaires before you get to the trillionaire, since we've only got one for the moment. Has been this concern that the tax that they're paying is not sufficient to represent, if you like, the incomes that they can get as a result of that wealth. And that's one of those sort of bone of contention, if you like. Are those billionaires contributing sufficiently to the economy, and does it just lead to huge inequality?
Because this is something really the tax system isn't set up to handle, is it? We're into this regime now where people basically realise money by borrowing it against something tangible that's grown in value for various reasons, and in this case a company has grown in value. Elon Musk owns that and borrows against it. There are many people in this situation where they've got money that falls outside the framework of what we know how to tax.
It does, but of course whoever lends to them has to take into account that the value of the shares may indeed fall quite significantly. So Elon Musk may not remain a trillionaire for very long, but on the other hand, he might become a multi-trillionaire at some point if things go well. So the real issue about being wealthy in terms of stocks and shares that you own, or a percentage of a company, which is in fact what's going on right now with all these tech bosses, is that it could all collapse.
So what sorts of conversations are economists and policymakers having around how we plan around that? Because I presume Elon Musk might be the first, but he's certainly not going to be the last trillionaire.
I just go back to what happened with the oil sector all those years ago when, of course, there was concentration of oil production in the US in one company, and the US government actually split them up into 7 in order to get more competition going. And that's the sort of thing which some people are saying we should do here as well. So stop the possibility of some of those sectors becoming oligopolies or even monopolies, and really sort of reduce quite significantly the power of one particular company and even one particular individual, if that is possible.
But you can't split Elon Musk 7 ways. Perish the thought.
Well, he seems to split himself 7 ways. So SpaceX has all sorts of other interest in it that rather than just space, as it says, mostly on the tin. And of course, he's very involved, or was involved, in politics and other stuff. So there is a concern that at a certain wealth level, you can also influence quite significantly what happens politically, domestically, and internationally. And you can move things in your favor because of that power. And that's the concern. So you can split the companies up. You could, I suppose. But also, I think it's interesting to remember that going back to the valuations we were talking about before and whether this trillions will still be trillions in a little while, that some of the firms that have made their part owners so wealthy haven't really been making any money yet. And that's what I think all of us whose pensions depend on proper investment and doing the right thing, if you like, for all these people who are getting older and will need some guarantee that they will be able to survive reasonably well in the future, may be in for a shock at some point.
What could you actually do with £1 trillion, though?
Can
you even spend that? I mean, if I started, how long would it take me to spend it? What would have to be my spend profile in order to get through that in a human lifetime? Is it even possible?
It's been calculated because people rather like that question and like to find answers to that. You could spend 1 million a day if you wanted, just like that. I mean, buy a few football clubs for anyone who's interested in that. After a few days, well, you may need to have 1 billion perhaps to do that. But, it mounts up. But if you spend 1 million a day, it takes you 2,740 years to spend your trillion.
Well, the way that the finances of many of us are going at the moment, that actually sounds like quite a nice problem to have. Economist and author Vicky Price there, and you can read our take on Musk joining the Trillionaire Club or even founding the Trillionaire Club over at nakedscientist.com/news. Give it a read. That's it for today. Tune in on Tuesday, though, when we're going to take a closer look at our ancient ancestors with some fascinating stories about how they buried their dead, evolved to defeat disease, created interesting cave art, and even made medicines and took drugs. If you'd like to get in touch in the meantime, it's chris@thenakedscientist.com/email. And if you can support the programme because you appreciate what we do for you each week, you can do that over at nakedscientist.com/donate. We'd be extremely grateful. I'm Chris Smith. Thank you for listening. And from all of us here at the Naked Scientist team, until next time, goodbye.